Hello students, welcome to Exam List. So in our last lecture we learned that if rho is constant for a fluid and if the fluid is moving through a pipe whose left hand mouth area is different from right hand mouth area, then by equation of continuity A1 V1 must be equals to A2 V2. That is, product of area and velocity on the left hand mouth must be equal to product of area and velocity on the right hand mouth. This was only true when the rho is constant. That is, rho is not a function of time or rho is not a function of space coordinates. What if our rho is a function of space coordinates? That is, rho is a function of x, y, and z. Now, what do you mean by a fluid whose density is a function of x, y, z? It means if you have a fluid, say let this be the fluid, the density is a function of x, y, z, tells us that the value of density of the fluid is changing with space. For example, if you take a small fluid element along this side and you calculate the density, you got density as rho 1. The moment you go to another fluid element somewhere around this side and at this point you calculate the density of the fluid, you found it was different. In such a case, the rho is a function of space coordinate. That is, at this point xyz, when you calculated the rho, and at this point when you calculated the rho, they are different. It means rho is a function of space. Rho is a function of space means at which point are you calculating rho. So if this is the condition, when rho is changing with space, then what the continuity equation tells us, let's try to derive. Okay, so first consider a control volume. Okay, that is, consider a small cubical section of liquid. Okay, and assume that liquid is entering from this direction and leaving this direction. Okay, so this is our first assumption. So what happens when the liquid enters in this direction and exits on the opposite direction? So let this direction be our x-axis. So one thing is clear, that rho is a function of space. So let this point be x, then this point is x plus dx. Okay, let me write it in this way: delta x plus delta x. Okay, so let's try to write the formulas. So what is the rho? So let me call this as side A and let me call this as side B. So what is rho at A? So rho at A is rho of x, and the value of rho at x plus dx, let me call it rho of x plus dx. Remember, rho of x is not same as rho of x plus dx. They are different values because now we are considering that the fluid has different density at different points. Okay, now we have to find out what rho of x plus dx is in terms of rho of x. So if you are calculating the density of the fluid at point B, then you find that it is equal to density of the fluid at x plus there is some change. This additional change tells you that rho is changing with space. So along x-axis, let this change be del rho by del x. So this is the rate of change of density along x-axis into delta x. Okay, it means that, you see, if this part were 0, if this additional part were 0, then it would mean that the density at point A is same as density at point B. The reason we included that extra part is to tell you that density at point A is different from density at point B. Agreed? Okay. Now, can you tell me what is the mass entering in the A side? So let me write mass in. So if you look carefully, the mass entering can be written as, so first write the volume. So how will you write the volume? So let's try to understand. So it will be written as, there will be velocity. So what is the velocity of the fluid? It is v into, so velocity is vx, that shows the velocity of the fluid in x direction, into dt. This is the time, so this gives you length. Then what is the area? Okay, so for considering area we have to consider this multiplied with this. Okay, so consider the length is given by delta y, dy, and this part is given by delta z. Then what is area? Then area is delta y into delta z. And then what do we need to multiply? We multiply rho. Very easy. But for completeness, I should write rho of x. Okay. Now, what is the mass out? How much mass is going out? To calculate the mass out, we have to do the same thing. So, can you tell me what is the velocity at point B? The velocity at point B, so consider velocity at point x is written as v of x. This is the velocity with which the fluid is entering. Velocity at point B is also going to be different. So let me write it as v of x, plus to show that velocity at point B is different, I need to add an additional part, which is rate of change of velocity of the fluid in x direction with respect to x into delta x. So what is m out? It's easy. So to calculate m out, first you write velocity into dt. So what is the velocity at P? It is Vx plus del V of x divided by del x into delta x. So this is my velocity at P. Multiply with time. Now you multiply with area. What is the area? Area is same, which is dy into dz. Now, what is rho? At final, we always multiply rho. So rho is rho plus del rho divided by del x into delta x. Okay, it's not difficult. Okay, so now if I ask you what is the change in mass due to the motion of the fluid along x direction. Okay, so this is a very bad way of writing. Anyways, so let me write delta m. So delta m is the change in mass in the control volume. By control volume I mean the cube. So the cube is just a fluid, okay, cubical fluid. So what is the delta m due to fluid motion? So due to fluid motion along x-axis, it is equal to mass in, which is rho into Vx, okay, into delta y into delta z. dt we will take common, okay. So this is m in, and what is m out? M out is a big term, which is rho plus del rho by del x into delta x. So this is the density at point B which is different. This is the velocity at point B, which is also different. Okay, and we need to multiply dy dz, and this whole thing can be multiplied with dt. Dt is the time. Okay, so this is a big term. Now this is only due to fluid motion along the x-axis. What happens if the fluid moves through this control volume along this z-axis, and what if there is motion of fluid along y-axis? Then we have to write the total change in mass in this control volume due to m in and m out in all these directions. Okay, so we will now look at change in mass due to fluid not only in x direction but in all directions. Or I can say the change in mass in the control volume due to motion of fluid in all the directions. So what will be the term for the y? Okay, let's see. For the y term, you should write everything is same, things will change. Rho Vy delta x delta z. Let me explain you this. So now we are considering the control volume again, which is a cubical part. Okay, and now we are considering that the fluid is moving along y. So this is in this direction. Okay, because we consider this as delta y. So now we are going to see what is the change in mass due to the motion of the fluid in y direction. Of course, if this is rho, then this is not going to be rho, but this is going to be rho plus del rho by del y into delta y. That is, the rho at both these ends are different. Similarly, velocity is also going to be different. So let me write the expression. So this minus, okay, here I should have rho plus del rho divided by del y into delta y. Agreed? Velocity is also different. What should you write? You write Vy. Because we are considering fluid moving in y direction, so let me call this velocity here is Vy. Then velocity at this point, at the lower mouth, is going to be Vy plus some change. That tells you that velocity is different. So this change is del Vy into dy into delta y. So that I need to multiply here. So let me write it as Vy plus del Vy divided by delta y into delta y. Okay, now here we multiplied area, so we need area terms here. So what is going to be area terms? It is going to be delta x delta z, and put the time outside. Okay, now the third term. The third term is going to be for the z direction. That is, if we are considering fluid moving in along this and going out along this, so the motion of the fluid along z direction is going to cause some change in mass in the control volume. So let's go and write this term. So this term is going to be, okay, big term, right? Now what you have to do is you have to evaluate this term. Okay, so let me write the result, what you get. So inside the control volume, the total change in mass due to the motion of the fluid along x, y and z direction is found to be minus, in bracket, we are going to have d by dx of rho vx. So this you will find after doing all the mathematics and cancelling the equal terms. Okay, plus d by dy of rho vy, and for the z direction we get d by dz along rho vz. Okay, multiplied with delta x, delta y, delta z, and there will be delta t. Okay, so what do you understand from here? So if you take the delta x, delta y, delta z, this makes up the volume. I can call it dv. If this dv goes down, then here we have delta m divided by delta v. Also take the small time dt here, I get this. So what is delta m by delta t? So this entirely is going to make the rate of change of density with respect to time. So rate of change of density with respect to time is going to be minus of del dot, I'm writing this big expression, okay, in shortcut. This big expression is del dot rho v. This v is the velocity distribution of the fluid. Okay, this we will do in next lecture. We'll understand why I called v as the velocity distribution with respect to space. So what do you see from continuity equation? The continuity equation now tells us that del rho by del t must be equal to minus of del dot rho v. V is the velocity field. Okay, now why I call the velocity as a field, and I can also call the density as a field. Okay, we'll discuss in next lecture, but you need to understand that if the density is changing with time, then the equation of continuity becomes this. But what can we do when rho is constant? Can we derive our equation of continuity for incompressible fluid from this equation? The answer is yes. We'll check out in the next lecture.